Hello friends, in the previous video, you would have already known that number one, for an object to travel in a circular path, like this picture, familiar, right? We need something to provide the centripetal force. So what you see here in the bottom picture is a top view of the car as it makes a turn. Okay, so what provides centripetal force here? The friction between the tires, okay, and the car. And I think you know, if you've watched enough shows or if you've driven a car before, you would notice that if you speed up too much or if the road is too slippery, the car will leave the circular path at a tangent. Okay, so we know that a condition or absolute must-have is that we need something to provide centripetal force. And in this case, right, it is straightforward enough because the road is flat and the car just makes a turn. But what happens when the road is not flat? Okay, so when I say the road is not flat, I mean the track is curved, and that would mean the track will look something like this. Okay, so example, the road is not flat, it is tilted. And you may be thinking, Miss, got road like that, meh? For good highways, they won't design the road this way lah. But who knows, maybe you are in a car park or in a ramp or some weird situation where you have to negotiate a turn. And you may be thinking that, Miss, wouldn't friction between the wheels and the car, you can see here, there's this arrow, provide centripetal force? Because whenever you want to know what provides centripetal force, right, step one is to determine the center of the circle. So like in this case, you see the center of rotation is here. So the centripetal force is directed towards the center of rotation. And if you look at this one, same picture, center of rotation is here. Let's say I call this C. Centripetal force is directed to here. But where is the center of rotation for this circular track? And if let's say you have problem imagining this 2D diagram, let me show you the diagram in 3D. All right, so let me scroll a bit. So this is a bank circular track. So you can see the car will travel at a circle, all right? And then the center of the circle is actually in this direction, okay? So directed towards the center of the circular path. So if we look at the 2D drawing of this, you know, going from this to this, it means that the center of the circular motion is not on the road, it is beside the car. Just like if you look at this one, this is on the road. See, the center of circular path is on the road. This one will also be, this one, the center of the circular path will be here. Okay, so this thing, if let's say you want to draw the circular path, it's going to be a bit of a stretch, but this thing will rotate in a circle this way. So there are a few things that you will notice. Number one, because the car is on the inclined plane, this means the normal force is no longer parallel to mg. Okay, so this one needs you to recap a bit about what you've learned in your dynamics chapter previously in your AS. So previously you know that normal must be 90 degree. So if you look here, this normal is 90 degree to the surface, the contact surface. In this case, because the contact surface is raised or the road is banked, your normal force will be at this direction, 90 degree to the inclined plane. Okay, so which means we need to do this thing called resolving vectors. Now, if you forgot how to resolve vectors, all right, think about this normal force and think about the purpose of this exercise. We want to find, okay, so let me write here, purpose. Okay, purpose. We want to see or to determine the net force or the resultant force, because the resultant force will provide centripetal force. So whenever you are lost in this kind of circular motion, they give you weird things that is moving in a circle until your brain begin to move in a circle. Think about the fact that we are actually looking for the resultant force, which will always translate to centripetal force. Okay, so in this case, right, I know the direction of the center of the circle is, let's say here. Okay, and if again you still struggle with imagining how this one is moving, I will show you a video later. Okay, so this one is still going to travel in a circular path, and the turn will look like the diagram that I've shown you just now. Okay, so just think about this one now. Okay, maybe it will help if I put this right beside. This is for the people who need it. Okay, but when we think about it in 3D format like this, right, it's very hard for you to resolve the forces, or at least it's a little bit hard lah. So I zoom in this way. Okay, but essentially we are drawing the same thing. Can So first step, determine the direction of the centripetal force, which is directed towards the center of the circle. Right? Okay, so I'll write down. Step 1. Find the center of, determine the center of the circular part. Okay? Step 2. The direction of FC is directed to this center. Okay, so this is the center of the circular part. It is here. So the direction of FC must be directed here. So I'm just going to draw this one. This is your FC, which happens to be your resultant force. And you may be thinking to yourself, why can't friction help? Well, in this case, you look at this diagram, weight is off. Weight is definitely not in the direction. Normal force is also not really in that direction. And you may be trying to say, why can't we rely on friction? Well, if you look at friction, right? If you think about friction, this car looks like it's about to slide down the inclined plane. So if there's any friction, friction will act up the inclined plane to prevent the car from sliding down. Does that make sense? So the car has a tendency to slide down. Friction is going here. Where's the center of rotation again? Center of rotation is here at the side. Okay, once again, center of rotation is here. Center of rotation is here. This direction, this is your C. So this friction is not really even in the direction. So I will write here, prevents car from sliding down the incline. So it doesn't help. The only thing that will help is this horizontal component of your normal force. Okay? So the only thing that can help your resultant force or can help provide centripetal force is the normal force, because the normal force is tilted towards the center of the circle. You see this tilt is in this direction. So we can naturally resolve this. So one component will be pointing up. I'm going to use maybe a slightly different green. Okay, so I will resolve the normal force in this direction because the normal force is pointing up. So this is your vertical component here. Okay, and then there's a horizontal component that is pointing in this direction. So this horizontal component is the one that provides centripetal force. I'm going to highlight here because you can see they are both in the same direction. So when I draw a double-headed arrow, this means that this one is resultant force. Resultant force. So this centripetal force is not a force that exists. Centripetal force relies on other forces to provide for it. In this case, mg is like I tap out, I can't help you at all because I am 90 degrees towards the center of the circle. So you got to imagine, for example, you have a circular track this way. Weight is pointing downwards, so cannot help, sorry boss. Well, weight is pointing downwards. What about normal? Normal is pointing in this direction. Maybe can help, okay? Because we can resolve normal like this and like this, okay? So normal can kind of help, but weight cannot. All right. And if you want to think about friction, friction is in this direction, also cannot help. Not really. In fact, friction will actually go against the direction of n. But for your syllabus and most cases, we will just assume that the friction is negligible lah. Okay. But in case you are doing more mechanics in your maths or anywhere where friction is relevant, you actually need to resolve friction. Okay, so this is a bit on the sidebar. You will resolve friction like this. So you may be thinking, wow, miss, many resolving. What is resolve again? Well, if you need this, okay, I will remind you again, whenever we resolve a vector, like in the case of this normal component, we are splitting the normal force that was 90 degree to the inclined plane here into a vertical component and a horizontal component. Okay, so basically, if I redraw this vector diagram, this one would mean that the vertical component, let's say I call this ny, y for vertical, plus the horizontal component. Okay, let me rearrange a bit. Vertical like this. Vertical component, ny, plus the horizontal component, nx. So this is ny, this is nx. When we total them together, or when we add them together, we'll get a resultant in this direction. This is n. Okay? If let's say I want to think about theta, where is theta? Well, my friend, if you want to find theta, okay, let me change up the colors a bit. If you want to find theta, then you need to use some right angle triangle already. Okay? So this one is 90 degree. Because it's mg. This one is also 90 degree because it's an extension of the normal force. Okay, and this angle here would be 90 minus theta, which means this angle here will be theta. All right, so if this angle is theta, because if you again slowly lah, you trace out the triangle. I'm using this triangle. Okay, so the reason why I know this is theta is because in this triangle, this angle is 90 minus theta. The reason why I know this is 90 minus theta is because if you trace out this triangle, so this 3D thing needs a little bit of time to slowly, especially if you are geometrically challenged like me. Okay, so anyway, this is my theta, and if this is theta, alternate angle lines, this will be theta. So that's how I know this angle here is theta. This is my theta. But how do I transfer this theta into the vector drawing, you ask? Well, this theta is between ny and the resultant component n. So this is my theta. You see ny pointing up, n pointing up and to the left. So this is the angle in between. So when it comes to resolving vector, all right, we will split up the components in such a way where n has two components that is 90 degree. All right, this, as you probably already know, this is very important for the study of mechanics, whether you are studying dynamics or you are looking at things that's moving. Because this thing is a vector, we want to be able to split the vector component to decide how and what force causes the motion that we are seeing right now. As per Newton's second law, if we don't know how the forces is moving, we cannot anticipate, where the forces is acting, we cannot anticipate how the object is moving. So sometimes we will try to find the resultant force to determine how the object is moving. But in this case, or the questions in this chapter, all the things are moving in a circle. So because it's moving in a circle, right, it gives you a clue. The clue here is that all the resultant force, I don't care lah, whether it's normal, it's mg, it's friction, will lead to a resultant force that is directed towards the center of the circle. This is what is meant by resultant force provides centripetal force. So let us go back to this one. And I'm assuming that this is a smooth road, okay? Smooth. And the car is moving relatively fast and there's no friction. So since we already got reminded on how to resolve this normal force, we're going to do this here. Okay. The normal force that is moving up here would be N. But how? Well, you think about how to find the length of this vertical arrow. Can I use maybe cosine? Okay. So if I look here, I can say cos theta is equal to ny over n. So the normal component that is vertical will be n cos theta. Okay, so this vertical component up here will be n cos theta. Okay, we're gonna do the same thing again, but for sine theta. Okay, I'm gonna write this here. Sine theta will be equal to opposite over hypotenuse. Look, you probably, hopefully have been doing this for a year or more. So I hope that this one comes second nature to you by now. All right, especially if you study physics, because you'll be doing it a lot, So I'm only going to show this once. All right, when you are beside the angle, because cos is side over hypotenuse, you will take n cos theta. When you're opposite the angle, like nx, and sine theta is opposite over hypotenuse, that's why you will take n sine theta. So oftentimes, hopefully you will develop the fluency to be able to immediately write n cos theta and n sine theta like this. Okay, so why are we doing this again? Why are we resolving this again? This is because my n sine theta is the unbalanced resultant, I'm going to hit all the keywords, force that provides Fc. Okay, let me zoom out a bit. So step 1, what did we do? We find the center of the circular motion here. Step 2, we look at the forces that we have. What force do we have again? We have the normal force in this direction. Okay, I'm going to draw this in black for you. We have this normal force here. The road is assumed to be smooth or friction is negligible. Okay, and the other force that we have is mg, which is here. So you have n, and then you have mg. Then what we did was we resolve. How do you know which direction and which force to resolve? Use the center of the circle as your guide. When you resolve the forces, one force will have an unbalanced component that is directed towards the center. Miss, who balance n cos theta? Why, my friend? That would be our good old mg. So n cos theta will balance with mg, and then this car will have an unbalanced n sine theta here. Okay, this unbalanced n sine theta is the one that provides the centripetal force and that is directed towards C. So this is your unbalanced resultant force that provides Fc. Important skill here. Please note that when we resolve forces, you should know how to split the force into one vertical and one horizontal. So one in the direction that you want, which is directed towards C here. This is the direction that you want. One is in the direction that is 90 degrees to the direction that you want, which is this n cos theta. Because when we split, it has to be 90 degrees. If not, then we can't use this, which is a pain. Okay, so go through the 3 steps. Find the center of the circular part. Okay, direction of Fc is directed to this center. And what is the 3rd step that we did? We look for resultant force, or find the unbalanced force. And when finding the unbalanced force, you might have to resolve. And this, another clue about the unbalanced force is it will be directed once again to C. So I've emphasized this quite a few times. You decide where the center of the circular part is, and then whatever forces that is available, see which one may provide centripetal force. Okay, so this is in 3D. I'll show you a quick video now, in case you need to see this actual thing in motion. So this is Azizul Hasni Awang, which is a Malaysian Korean cyclists, I want you to first, before I start playing, okay, I want to mute this, to notice the track. Okay, notice that the track here is banked. Okay, the track here is banked, is at, this side is flat, this is horizontal. The referee is horizontal. The people is all horizontal. Okay, and the cyclists are on the bank track. Okay, so in this K-ring race, which is generally an acceleration race, when the bicycle will already be on the track, and then when the bell rings, they have to accelerate lah. Okay, so let's see. So the bell has rung, and you can see from here that this track is curved and they are tilting towards the center. Where's the center of rotation here? The center of rotation is somewhere here because the curve is like this ma, in 3D. Can see my mouse or not? The curve is like this. So the center of rotation is here. So if you're leaning towards the center of rotation, your normal force that is directed in this direction will have a horizontal component. Okay, I will crop a closer picture for you. So you can see they're actually tilting very severely before moving straight again. And then when they want to turn, when they want to make a corner, they will tilt. You see it's tilting? Okay. So this is important because the center of the circle is here. Let's do the 3-step exercise again. How do we decide the center, the direction of the centripetal force, and what do we do? Okay, let's see. Now. Okay, I got the picture on OneNote again. So again, what skills are we trying to practice today? We're trying to look at situations of circular motion where things like a bank track will cause what provides the centripetal force. So what was our step again? Step 1, find C, center of the circular part. So you can see our friends here are turning in a circle. Okay, so the center is, I'm guessing somewhere here lah. I don't know where the center is, but I know the direction of the center is here. This is the direction. Okay, when they are in this position lah. Okay, so now let's draw the forces acting on our cyclist law. We have mg that is always pointing downwards. So if they are not moving in a circle and they tilt their bicycle this way, confirm will fall down one, right? The mg will exert a downward moment, downward resultant moment, and then it will just fall down. But thankfully they are moving in a circle and something else is balancing mg. All right, what else do we have? We have normal force, and normal reaction should be, okay, I don't know whether you can see, but this is the wheel, guys. I know a bit pixelated, but this is the wheel. So the normal force will be parallel to the wheel, okay, and directed upwards like this lah, through the head. Oh, like that like that. Okay, so what we gotta do is we gotta resolve the normal force. Okay, so if you've watched the front part of the video, you will notice that what we'll do is we will split this normal force such that there is a component that is directed towards the center. That will be step 2. Okay, so I'm gonna write here. Step 1. Okay, now let me break down the steps even more. Find C. Step 2. Label all forces. Step 3. Find component, or components could be more than one, of force that is, number 1, directed to F, to the center of circle. So this is why the first step is to find the direction of the center of the circle. It is the North Star, okay, of your drawing. Number 2, you will determine what is unbalanced. Because this unbalanced force provides net force, which is equal to centripetal force. All right, so that's the main concept, skills that you can have, because sometimes it can be a bit more complicated. Okay, so here there will be a normal force, and as we have done before, I'm going to resolve our beautiful cyclists again. I mean, not resolve them, resolve the forces acting on them. you will have a component that is vertical, and you have a component that is horizontal directed towards the center of the circle. Okay, and if you remember, this was our theta. Okay, so here will be n cos theta. This is n sine theta. So hopefully with this diagram in context, you will understand that n cos theta is the one that balances mg to prevent the cyclist from falling to the side. Plop. That'll be not very good. So this n cos theta will balance with mg. Okay, and what about this n sine theta? This n sine theta is your unbalanced net force. So because it's unbalanced, how do you know it's the unbalanced net force that you want? Well, because it's directed towards the center of the circle. Center is here. So the center is actually telling you how to resolve the normal force. So whenever you see a normal force, look at all your forces. Who could we possibly resolve so that the force is directed towards the center? Okay, so this one will provide centripetal force. So that's the conceptual understanding. You may need to actually look at different scenarios, okay, to determine how to resolve the forces lah. But I'm going to end this video